Okay, the last problem that we're going to be doing this evening and in this section that has to do with projectiles is going to be problem 1111. So for this problem, we have a projectile that's going to be fired with an initial velocity of 800 feet per second, okay, at a target B that is located 12,000 feet horizontally and 2,000 feet vertically from its original position, okay? Neglecting air resistance, determine the value of the firing angle alpha that is needed to hit the target, okay? That is needed to hit the target. So we're gonna be using that section of our equation sheet that deals with the projectile motion. Okay, so as we look here, we're going to kind of organize the information that we're given, and look what we have to find. So sample 1111, and as we're doing these things, the problems aren't asking for diagrams, but not all the problems that we do diagrams, but I always want you to have a section at the very beginning of any problem that you work, especially for the homework, of what your givens are and what you're trying to find. Okay, because then you know where you're going with the problem, and then if an illustration seems to make sense, then add it. And sometimes they do. Sometimes they do. So I am going to put a little illustration here, and it's going to just be that point A. Okay, here we've got a horizontal line, and it's going to be all the way over here. Okay, and we're going to go up to point B, which is our target. Okay, and we know that distance is 2,000 feet above, and that is going to equal our y distance, okay? And then we know that from A to B horizontally, this is going to be 12,000 feet, and that's going to equal our x distance. Okay. We know that this is going to follow this path, something like that, okay? And that means that this is going to be shot up at an angle, okay? The initial velocity is 800 feet per second, okay? And we don't know the angle. We don't know the angle. So alpha is what we're going to have to find, okay? Now we do know that this is going to have an x component, so this is going to be our VOX, okay? And it's going to have a y component, a VOY. Something like that. We know that gravity is also going to be affecting things. So I'm just going to put acceleration of gravity is equal to, okay? Now, if we look at our units here, they're feet, right? And seconds. So we're in English units, all right? So that means that our acceleration of gravity is going to be a negative 32.2 feet per second squared, okay? And I'm going to put our convention up and to the right is going to be positive, okay? And what we need to find is alpha. So what is the angle that we're going to, put this in so that we hit our target, okay, that we hit our target B. So that's our problem. These are kind of the things, okay? So first of all, conversions. Does it look like we need to convert anything? So my little symbol here, this is feet, okay, and this is feet. Acceleration is in feet per second squared. So it looks like we're consistent units across the board. So we're in feet and seconds. So we don't need to do any conversions, which is good, So we can jump in right away, and we know we're going to have to do the components, right? So we're going to do the components of V0, or our initial velocity. So our VOX, the horizontal component, is going to be equal to our original velocity times the cosine of alpha. Again, we don't know that angle yet. That's what we're going to be solving for. So our horizontal component of that velocity is going to be 800 times, I'll just put cosine, I don't need a parentheses, times cosine of theta. No, alpha, not theta. So I'll just go like this. That's our value. And then we're going to do the y component. And that's going to be times the sine of alpha. So our value is going to be the 800 times sine alpha. Those will represent the x and the y components. Okay. So we just leave them in that form. Step number two, let's look at the horizontal motion to start. Okay. So the horizontal motion. Now, horizontal motion. We know that horizontal motion for a projectile is always going to be constant velocity, so there is no acceleration. And so these are the equations that we get to deal with. We know that that is going to always be consistent throughout. Okay. So this is constant velocity. And I like to just identify that and get my mind wrapped around that so I know kind of where I'm headed and what the relationships are and how it's going to behave. Okay. So we can use that 12,000 because we know that we have to cover 12,000 feet, okay, horizontally. All right. And we know it's going to be starting at this velocity. We don't have a number, but we can put it in terms of its angle. So we're going to say that that distance is going to be equal to our original velocity in the x direction times the time. Okay. So rearranging this for time, okay, equal to our x distance divided by our x component of that velocity. It's equal to, we know that that x distance is 12,000 feet, and we're going to divide that by 800 cosine alpha. So we can reduce this by taking 800 and dividing it into the 12,000. So we can say that our time is going to be equal to, if we take 800 into 12, it's going to be 15. So this is going to be 15 on top divided by cosine alpha. Okay, so that's going to kind of sit out here. And that's really all. I mean, there's no acceleration, and the velocity in the x direction is that over the entire projectile. So this is where we have to kind of leave it, right? And we'll use that in just a little bit. So now we're going to do our vertical motion. This is where it gets fun. Now, our vertical motion, we know that that is going to be constant acceleration because that's the component that's always affected by gravity pulling down on it, right? Okay. So this is going to be constant acceleration. Okay. And we know that the gravity is going to be English units 32.2 going down. Okay. So as we look at our equations, the first one we're going to look at is, we'll pick the distance equation to get started. So we're going to use this one right here. All right. So we've got y. It's going to be equal to our y offset from the origin. Our origin for this problem starts at A. So, I mean, it's not identified, but yes, indeed, this is our 0. Okay. So that means that this is going to go to 0, right? Oh. It's going to be plus our original velocity in the y component times the time, okay, that we're looking at, plus 1/2 acceleration due to gravity times time squared. Okay. Now, because we have the time up here, all right, horizontally and vertically, that's the total time. We can use that and we can put it into, substitute it into those t's there, okay? So as we look here, our y distance, if we look up here, the y distance is going to be 2,000, okay? So we're going to put 2,000 up front. It's going to be equal to our y component of our velocity. Our y component of our velocity is right here. It's 800 sine alpha times the time. That's right here. That's times 15 divided by cosine alpha. Whoopsie. Cosine alpha. Okay. Then we're going to have plus 1/2 times, remember, this is a negative 32.2 feet per second squared, okay? Negative because it's pointing down, times t squared. Our t is this, so this is going to be 15 divided by cosine theta squared, all right? Now, trig identities. Before we kind of go through this business here, let's kind of remember those, all right? So we know that, and I'm just going to put a where, this is going to be kind of like a little bubble by itself, okay? We know that sine, I'm going to use alpha, divided by cosine alpha is equal to tan alpha. That's a trig identity, okay? I'm not expecting you to remember those. I'm telling you, but if you want to look them up and recall, you know, what those are, they don't come up all the time, but periodically I'll remind you of those. But yeah, that's a trig identity. Okay, so that's going to help us out here. All right. And then the other one that we have is this one. Okay, so this is a 1 over cosine squared, right? So if we, or cosine squared alpha. So if we look, this is going to be a 1 over cosine squared alpha is equal to a secant squared alpha. Oops. Here. Oops. And a secant squared alpha is a 1 plus tan squared alpha. Okay. Now, I don't remember these, you know, because I don't visit them quite that often. So like I said, it's always okay to, you know, look back or look at a resource and make sure that you got the right thing. So we're going to be using this. So we've got a cosine squared alpha here. That's a secant squared alpha. And we're going to be, you know, substituting this value just a bit. So I'm going to kind of put a little cloud around this because this isn't part of the problem. These are our identities that we're going to be using in here. Okay. So down here, I'm going to grab, I'm just going to leave the 2,000 out front. It's going to be equal to 800. Okay. Sine, wait, no, 800 sine alpha times 15. Sorry, I'm looking at the wrong line here. So we're going to multiply that by 15. Okay. And because sine alpha divided by cosine alpha is tan alpha, we're going to do tan alpha. Okay. So that's this with the trig identity in there. Is that helpful? You guys see that? Okay. Minus, okay. Now this is going to be 1/2 times negative 32.2. Okay, that's going to be 16.1. Okay, that's that. Times, so we're going to multiply that by the top line here, 15 squared. Okay. And then we know that under the radical here, okay, we're going to multiply that by 1 plus tan squared alpha. Okay. Now, the reason we wanted to do that is we now, instead of having sines and cosines, we've got only tangents. Okay, so that's a good thing. So let me combine a little bit more here. All right, so we're going to multiply this out. We're going to say, I'm just going to leave it on this line right now. So I'm just going to get this into my numbers. So 800 times 15 is 12,000 tan theta minus 16 times 15 squared. Okay. It's going to be 3622.5 minus, now I'm going to take this and I'm going to multiply it here times the tan. So this is going to be 3622.5 times tan squared alpha. Okay. So this is this times 1, and this is this times tan. And because there's a negative out front, they remain negative. Okay. I'm going to just make sure everybody got that line there. Does it make sense how that worked out? So this is distributed into this. So this is that one first times 1 plus this times the tan squared alpha. Okay. So now I'm going to take my 2000 and I'm going to push it to the other side. Okay. So this is going to be 0 is equal to. Now, as I'm writing this out, you're going to notice that I have a tan squared and I have a tan, and then I'm going to have some constants. This is going to be in a quadratic form. So what I'm going to do is I'm going to put this in that quadratic form. Okay, so I'm going to take this tan squared alpha and I'm going to bring it to the front. So this is going to remain negative 3622.5 tan squared alpha. Okay, so that's my first one. It goes to the front. My second one is going to be my 12,000. So that's going to be plus 12,000 tan theta. Okay. And then this 2,000 is going to be negative on this side, right? So if this is negative, it's going to add as a negative to that. So that's going to be negative 5622.5. Okay. Does that make sense? So now this is our quadratic form. Okay. So this is quad form. And so we're going to have this with the square, this with the non-square. So this is my A, this is my B, and then this is my C. Okay. Okay, so let's go over there to see what we find for our values of 0. So I'm going to go back to Excel over here, and I'm going to do the negative 3622.5, then 12,000, and negative 5622. There we go. Okay. So you should get these decimals. Or I'm sorry, the decimal, the 0.564 and the 2.75. Okay. Those are our two numbers. So go back over here. Now, because I'm sorry, I'm going to go back one more time. Because neither one of these values is negative, that means that we have two valid values for our angle. And what that angle is, the angles are not these, okay? The angles are not those. So our numbers are, we're going to say tan alpha is going to be equal to, this is the decimal of 0.565. So you are going to take the inverse tan function of 0.565, and that will be the angle. So 0.565 inverse tan, you should end up with alpha equal to 29.5 degrees. That's one of the angles, okay? And then the other one is going to be tan theta equals 2.75. Okay, so then you're going to take 2.75 inverse tan, and that's going to be 70 degrees. So what that means is we can actually put our projectile at two angles, about 30 degrees and about 70 degrees, and we're going to hit that target both times. Isn't that interesting? So I'm going to leave this up here because I'm, if you gotta kind of, there's a lot to follow along there. So I'm going to let you kind of digest that and make sure you have everything. But that is the final answer for this problem. Very practical problem, honestly. I mean, if you have a location and you want to try to hit a target, what is the angle I have to put this at? Okay, so that's kind of cool. All right. If there aren't any questions, which doesn't seem like it, I'm gonna stop the recording here.